Dear students, today's lecture is on Codal provisions for design of PSC member. In that, we will see design for flexure, design for shear, and design for torsion. Now, in last lecture, we saw the determination of losses in PSC member. Now, today, we'll see design part. Now, the design is based on following assumptions. Which are these assumptions? The first one is plane section before bending will remain plane after bending also. Concrete is a homogeneous elastic material. Third one, within the limits of deformation taking place, Hooke's law is applicable to concrete and steel components. And the last one, variation of stress in the reinforcement due to changes in the external loading is ignorable. Almost all these assumptions we use even for RCC structure. But now, what are the values of modulus of elasticity of steel? If you see, according to old code, that is IS 1343/1980, three different types were given. In that, plain cold drawn wires, for which the modulus of elasticity was given as 210 kN per mm square. For high tensile steel bars, it was 200 kN per mm square, and for strands, it was 195 kN per mm square. But now, according to the revised code 1343/2012, the value is common, and that is 200 kN per mm square. There is one more change in the new code, and that is maximum initial pre-stress. It means this is the stress which we provide to the wires, that means during the jacking. So according to old code, 80% of FPU means it's the ultimate tensile strength of wires or tendons or strands. So 80% of that can be applied, but according to new code now, that value is reduced to 0.76 FPU. That means only 76% of ultimate tensile strength of wires. Well, tensile strength of concrete, it is same as that of IS 456, and that is equal to 0.700 of FCK. And modulus of elasticity of concrete, it is also same as that of IS 456, and it is 5000 under root of FCK. Now, next table is for grade of concrete. So, in IS 1343, grades are mentioned from M30 to M80. Well, for pre-tension PSC, the grade of concrete shall not be less than M40. So, is the minimum grade of concrete. Already we know that. Okay. Well, and M30 is the minimum grade for post-tension. Then M30 to M80. So, this 30 Newton per mm square, it is the characteristic compressive strength given by cubes of size 150 by 150 by 150 mm at the end of 28 days. Well, one more note is given in the IS code that for concrete grade greater than M60, design parameters given in the standard may not be applicable, and the values may be obtained from specified or specialized literature and experimental results. It means whatever the tables are given is are only up to M60, that means like permissible stresses and all these things. So above M60, if you want to take the values, then you have to refer the literature for that one. Now, the requirement of nominal cover to meet durability requirements. Now again, it is divided into two parts: post-tension work and pre-tension work. So the minimum clear cover for sheathing or duct shall be at least equal to the diameter of the sheathing and duct or duct. And for pre-tension work, the cover of concrete measured from the outside of the pre-stressing tendon shall be as per table 16 of IS 456. Now, in this table 16 of IS 456, you will find that the different environmental conditions are given. And which are these different environmental conditions? Like mild environmental condition, the cover is 20 mm. For moderate environmental condition, the cover is 30 mm. For severe, it is 45. For very severe, 50. And extreme, it is 75. So, this table is to be used for pre-tension work. Now, what about spacing? Spacing between the tendons or spacing between the ducts. In case of single wires used in pre-tension work, the minimum clear spacing shall not be less than greater of the following. So, first 3 times diameter of the wire, and second nominal maximum size of aggregate plus 5 mm. That means if you are using maximum size of aggregate of 20 mm, then 20 plus 5, 25 mm. Okay. So, whichever is greater out of these two, that we have to use for spacing in pre-tension work. Well, in case of cables or large bars, the minimum clear spacing measured between sitting ducts wherever used shall be less than the largest of the following: 1. 40 mm, second, maximum size of the cable or bar, and third, maximum size of aggregate plus 5 mm. Okay, so whichever is higher, that we have to use. So this is regarding the spacing. Now, grouped cables. If the cables are provided in groups, then what is the criteria? The minimum clear horizontal spacing between groups of cables or ducts of grouped cables shall be greater of the following: A. 40 mm, B. nominal maximum size plus 5 mm. Okay, so this is for group cables. Now, what about the vertical distance? The vertical distance between groups shall not be less than 50 mm. That means the clear distance between the vertical ducts. In case there is possibility of obstruction of flow of concrete, or in case of severe exposure condition, horizontal grouping should be avoided. That means in case of severe exposure condition, or when there is a possibility that there is a lot of congestion of the ducts and the reinforcement, then obviously the horizontal grouping shall be avoided just to have proper concreting. Okay. Now, whenever we start any design, we have to think about permissible stresses. Okay. Now, according to IS 1343, first we have to decide whether we are designing the structure as a type 1 or type 2 or type 3. Now, what is this type 1, type 2, type 3? Type 1 is the structure where no tensile stresses are allowed. That means at the bending phase, there shall not be any tensile stress. The resultant stresses must be under compression. Type 2, in that some tensile stresses are allowed. How much? So the tensile stress shall not exceed 3 MPa. That means it's minus 3 Newton per mm square, okay, at the bottom phase. However, part of the service load is temporary in nature. This value may be exceeded by 1.5. That means if some part is temporary, some part of the load, if it is temporary, then you can increase that value from 3 to 4.5 Newton per mm square. But one more condition is given: provided under the permanent component of service load. That means whatever the permanent load is there, the stress remains compressive. That means the whatever the minus 3 value is allowed, okay, that is not acceptable under the permanent component of service load. It means it must be 0 or its positive side, that means compressive side. In type 3 structure, cracking is permitted. Well, but cracking is permitted, that totally depends on the width of the crack. When cracking is permitted, that should not affect the appearance and durability of the structure. It may be assumed that the concrete section is uncracked and that hypothetical tensile stress exists at the maximum size of crack. Use tensile stress given in table number 10, and again you have to modify it by using figure number 6. Now, what is this table number 10? On the next slide, we will see this table number 10. In table number 10, this hypothetical flexural tensile stress for type 3 structures are given. Now, in this, for pre-tension tendons, for group post-tension tendons, and third one is for pre-tension tendons distributed in the tensile zone. Well, for each criteria, each type of the tendon, the limiting crack width is given like 0.1 mm, 0.2 mm, again 0.1, 0.2 like this, okay. And for each limiting crack width, for different grade of concrete, the values are given. For pre-tension tendons, since M30 and M35 is not allowed, so it is M40, M45 and M50 above. This is the value of the permissible tensile stress. So likewise, for different members, it is given. There is one note which is given. It is related to additional reinforcement. When additional reinforcement is distributed within the tension zone and positioned close to tension phase of concrete, the hypothetical tensile stresses may be increased by an amount which is proportional to the cross-sectional area of the additional reinforcement, expressed as a percentage of the cross-sectional area of the concrete. That means in percentage you have to express that additional reinforcement, and if that additional reinforcement is 1%, then the stress may be increased by 4 Newton per mm square for members with pre-tension and group post-tension tendons, and by 3 Newton per mm square for other members. For other percentage of additional reinforcement, the stress may be increased in proportion, excepting that the total hypothetical tensile stress shall not exceed 0.25 times the characteristic compressive strength of concrete. So this is the limitation condition which is given for that one. Okay, so this table is for type 3 structures. Now there is one more figure which is given for the modification. Now that depends on depth factor for tensile stresses. Now here the depth of the member is given, and according to depth of the member the depth factor is given. So this is the multiplication factor to the permissible stress for type 3 structure. Well, now the earlier table number 6 which we saw, sorry, table number 10 which we saw, that is related to tensile stress in concrete. Now we'll see compressive stress. Now in compressive stress, the notation is used as FCT. So here F means the permissible stress, C stands for concrete, and T stands for transfer. So there are two cases here which are considered: initial stage and final stage. Initial stage is also called as transfer stage, and final stage means when the structure is subjected to all the load, that is dead load and live load, when it is under service condition, that is the service condition. Well, now the compressive stresses FCT we can determine from these two figures. Figure 8E is for post tension work and figure 8B is for pre tension work. In both the figures you will find the values are given in proportion with FCI value. For example, for M30 for post tension work, the compressive stress FCT is given as 0.5 for FCI, and which reduces to 0.37 FCI for M60 grade of concrete. Similarly, for pre-tension work, for M40 grade of concrete, that value is given as 0.51 FCI, and which reduces to 0.44 FCI for M60 grade of concrete. What is this FCI? FCI is the strength, compressive strength of concrete at transfer. That means whenever you transfer stresses to the concrete, in pre-tension work, we cut the wires. That means the stress get transferred from wires to the concrete, and in post-tension work, we provide tensioning operation. We provide tensioning to the wires. So that the strength on that at that time, that is called as FCI. Well, so these values are given in terms of FCI. Well, for in between grade of concrete, we can do interpolation. Now this is the stresses at transfer. What about the compressive stresses at final condition? So final condition is FCW. Here F means permissible stress, C means in concrete, and W means at working condition. Well, working condition or service condition. Now here in this graph, the two zones are given, zone 1 and zone 2. Now what is this zone 1 and zone 2? So very simple thing, you have to remember that when the compressive stresses are not likely to increase in service span in part of the section, then adopt it as zone 1 structure. And if there is possibility that the compressive stresses are likely to increase in the service span, that means the loads are not fixed, you cannot predict about that, then just go on the little bit conservative side, and that's why zone 2 is given. So zone 2 values are lesser than the values for zone 1. Now here for zone 1, again the values are given in terms of FCK. For M30 to M60 linear variation is given. So for M30 it is 0.41 FCK, which reduces to 0.35 FCK for M60 concrete, and for zone 2 it is 0.34 FCK, which reduces to 0.27 FCK for M60 concrete. So zone 1 values are on the higher side and zone 2 values are on the conservative side. Well, acceptance criteria. Now acceptance criteria means whenever we construct the member later on, the actual application of the loads we can do, and whether the structure is accepted or not, for that some clauses are given in IS 456 also, and which are extended here in IS 1343. Well, so the provision of IS 456 which is given in clause 17 shall apply except for the following. So all the sub clauses which are given in clause number 17, these are applicable except clause number 17.6.2 shall be limited to full dead load of the structure plus design imposed load. So this is not applicable here. Remaining clauses are applicable. Now then, which point is applicable instead of this clause? So again, two sub points are given here. For type 1 and type 2 structure, if within 24 hours of removal of the imposed load, the structure does not recover at least 85% of the deflection under superimposed load, the test may be repeated after a lapse of 72 hours. And if the recovery is less than 90%, the structure shall be deemed to be unacceptable. So this is related to the recovery of the deflection. And for type 3 structure, if within 24 hours of imposed load, the structure does not recover at least 75% of the deflection under superimposed load, the test may be repeated after a lapse of 72 hours. If the recovery is less than 80%, the structure shall be deemed to be unacceptable. So these are the additional 2 points which you have to remember for the inspection and testing of structure. Now, one more very important part is related to deductions for pre-stressing tendons. Because when individual tendons are provided, there is no problem. But when ducts are provided with some diameter 70 to 100 mm or even more than that, then there is a question whether to reduce that area or not. So some points are given related to this. Let's see. The deduction for pre-stressing tendons shall be considered for the determination of area, centroid and moment of inertia of the cross section. Now, first we'll see for pre-tension members. In pre-tension members where the pre-stressing tendons are single wire or strand of relatively small cross-sectional area distributed on the cross-section, allowance for the pre-stressing tendons need not be made. That means don't reduce any area. Where allowance is made, it shall be on the basis of m-1 times the area of the pre-stressing tendons. M means it's a modular ratio. So it's the ratio of ES divided by EC. In case of post-tension members, deduction shall invariably be made for pre-stressing tendons, cable ducts or sheets and such other openings whether they are formed longitudinally or transversely. These deductions need not, however, be made for determining the effect of loads applied after the ducts, sheets or openings have been grouted or filled with concrete. That means if all these ducts are grouted, then don't subtract such area. But if such deductions are made, the transform area equivalent to m-1 times the area of the pre-stressing sheet shall be taken in the calculation. Now, in the third point which is given is, in case of multi-directional pre-stressing, the loss of area due to presence of ungrouted ducts, sheets placed at an angle to the pre-stressing tendons under consideration may be made at full area 100% of such ducts because these are ungrouted. In case such a ducts placed at an angle have been grouted prior to stressing of tendons, 50% of the area of such a ducts can be considered as effectively available. So only 50% if grouting is done. Well, so this is the criteria related to deductions of pre-stressing tendon. Now, for the design of flexure, again we have to see the partial safety factors. So when assessing the strength of the structure or structural member for the limit state of collapse, the values of partial safety factors gamma m should be taken as 1.5 for concrete and 1.15 for steel, and these are the same as that of RCC members. So this is the table for limit state of collapse, the factor, and this is limit state of serviceability. These are the factors. All these values are same as that of IS 456. Well, now for concrete, what type of stress block diagram is given by the code? So here the stress strain curve for concrete. Now here we'll consider three curves. The top curve is the actual curve when we test any cube. So whatever the stress strain diagram we get, so this is that parabolic curve. Well, this value FCK is reached to 0.67 FCK. So this is called as design curve. That means this is the strength given by concrete in the member or at site. Well, so this is the from FCK to 0.67 FCK, this is the reduction. And when we divide it by factor of safety, partial factor of safety for materials, that is 1.5, then we get this curve. So 0.61 FCK divided by gamma m, and that is 1.5. So we get this third curve. So we consider this third, the bottommost curve in the design. Well, this is the stress block diagram given by IS code. So here XU is the depth of the neutral axis. 0.4 XU is the depth of total compression from top face, and this is 0.36 FCK into XU. It is the total compressive force. This stress block diagram is same as that of RCC section, and we use which is given in IS 456. Well, now whenever we design any member for flexure, then we have to check the moment of resistance against the actual bending moment. So how to calculate moment of resistance for rectangular and T section? Now in IS code, for T section, when the neutral axis lies within the wave, so that portion is ignored, and directly we have given only one single equation, that is for the rectangular section, or you can say for the flange portion of the T or I section. Now mu, so it is moment of resistance, we can use R here, okay, but in IS code mu is given F suffix PB multiplied by APS, A suffix PS in fact, D minus 0.42 XU. What is mu? Mu is the moment of resistance of the section. FPB is the tensile stress in the tendon at failure. How to get this? We'll see the table which is given in the next slide. FPE is the effective pressure stress in the tendon. APS is the area of stressing tendons in the tension zone, and X is the neutral axis depth. Well, there is one note which is given here. It shall be ensured that the effective pressure stress FPE, that means this value, after all losses is less than 0.45 FPU, where FPU is the ultimate tensile strength of steel, where FPU is the characteristic tensile strength of tendon. The stressing tendons in the compression zone should be ignored in the strength calculation when using this method. That means when you are using this method, APS value you are calculating, in that case you just ignore the stressing tendons in the compression zone. Now, how to get these values? So for that you have to refer table number 11. In table number 11, first you have to determine this value. So what is this value? It is the area of steel, APS multiplied by FPU, that is the tensile strength of steel. BD, now this is the width, D means depth, and FCK. So for rectangular section, B means actually it's the width of the rectangular section, but in case of flange section, B is the width of the flange, BF. Well, and for that you can calculate the value of FPV by getting first this value, and for the corresponding what are the factor is given, that you can equate to this value and we can find the value of FPV. So for column number 3 is given for pre-tensioning and column number 4 is for post-tensioning. Well, now this equations gives you FPV and this equation gives you the value of XU. So XU by D, once value we get multiplied by D, we get the value of XU. This is the depth of neutral axis. Well, now the earlier slide was related to flexure. The next slide is related to limit state of collapse, shear. Now here the shear, that means the shear capacity of the section is to be considered from the less value from uncrack and crack in flexure. Well, so this is section uncrack in flexure. So this is the equation VC0 is equal to 0.67 BD under root of FT square plus 0.8 FCP into FT. Now here B means is the width of the member, and in case of I section or T section it is width of the wave. D means overall depth of the member, and FT it is the maximum principal tensile stress and the value is constant, that is given by 0.24 under root of FCK. FCP is the compressive stress at central axis due to stress taken as positive. Well, it is simply P by A because it is at central axis, so only P by A will act here. Well, substitute the values here and we get the value of VC0, and that is the ultimate shear resistance of section uncracked in flexure. The next equation is given, that is the section crack in flexure. Now, what is the equation? It is VCR is equal to 1 minus 0.55 multiplied by FPE divided by FP. But outside the bracket it is tau C into BD plus M0 into V by M. Now, more terms are given here. So, FP is the effective stress after all losses have occurred, which shall not be taken greater than 0.6 FP. So, you cannot take more than this one. Okay. The FP is the characteristic strength of steel. Tau C, it is nothing but the shear stress. Okay. So for shear stress, the table 8 is given, and from that you can find the value of tau C. So B is again width of the member, and for flange section or T section, it is the width of the wave. D is the distance from extreme compression fiber to the center of the tendons at the section considered. M0 is the moment necessary to produce zero stress in the concrete at depth. How do you find this M0? So for that, one more equation given in IS code. So that is M0 is equal to 0.8 FPT I into Y. So where FPT is the stress due to pre-stress only at depth of D and distance Y from the center of the concrete section which has the second moment of inertia I. So of course some calculations we need to do here. V and M, it is the shear force and bending moment at the section considered. One more condition is given, that whatever the value you will find VCR, that should be taken as not less than 0.1 BD under root of FCK. So this is the condition which is given. Okay. Now, since we saw two equations, okay, one is this VC0 and second one is this VCR. Now, what the condition says? The ultimate shear resistance of the concrete alone, VC, shall be considered at both conditions, uncrack and crack and fracture, the lesser value. That means out of these two equations, whichever value is less, that you have to consider. Okay. So after getting the value of VC, that means the lesser value, what next? When VU is less than VC, VU means actual design shear, the actual the design shear, VU. When the VU is less than VC, the shear force is carried by concrete. Hence, minimum shear reinforcement should be provided. So this is the equation same as that of RCC. Okay, ASV divided by B into SV, that is equal to 0.4 divided by 0.87 Fy. So where ASV is the area of shear legs, SV is the spacing, B is the width. Then Fy. Now this is Fy is the tensile strength of shear reinforcement. Okay, it is not the pre-stressing reinforcement, it is the shear reinforcement. That means Fe415, which we have to consider here. Well, now, however, if shear reinforcement did not be provided in the following cases where VU is less than 0.5 VC, that means the design shear force is quite less, that less than 0.5 VC, and in the members of minor importance, it is not necessary to provide any shear reinforcement. And when V, that means when the shear force exceeds VC, the shear reinforcement shall be provided, that means the design shear reinforcement. Okay, and what is that equation? It is ASV divided by SV is equal to V minus VC divided by 0.87 Fy into dt. Well, so dt, that is the distance from extreme compression fiber to the center of the shear reinforcement at bottom, or the longitudinal reinforcement, whichever is higher, that we have to consider it as dt. The spacing of stirrups shall not exceed 0.75 dt nor 4 times the wave thickness for plain section. When V is greater than 1.8 VC, that means very higher value, the maximum spacing should be reduced to 0.5 dt. So from 0.75 dt to 0.5 dt. Okay, so it's quite less value. The lateral spacing of individual legs of the stirrups provided at a cross section should not exceed 0.75 dt. Okay, this is the lateral spacing of the individual legs. Individual legs means if it is 3-legged, 4-legged. Okay, so for that also the criteria is given. Now, limit state of collapse torsion. Well, though according to some universities, the limit state of collapse torsion, this part is not considered, but till we'll see what the IS code is saying about this torsion. Now, when it is necessary to design the section for torsion, so for that, IS code says that beams of solid rectangular section where depth of the beam is greater than width, then it is necessary. For hollow rectangular beams with D is greater than B and with a wall thickness T is greater than or equal to B by 4 and all T beams and I beams. In all these cases, the average intensity of pre-stress in the concrete shall be less than 0.3 FCK. Well, now when we are designing it for torsion, first we have to design longitudinal reinforcement and then shear reinforcement. So for longitudinal reinforcement, you have to calculate equivalent ultimate bending moment, and that is equal to ME1, which is nothing but M plus MT. So M is actually, it is the applied ultimate bending moment due to dead load and live load, and MT is the torsional moment. How to find that moment? So MT is equal to T, where it is the torsion, under root of 1 plus 2D plus B. Well, the sign of MT being the same as that of M, that means the signs are same. Okay, if they are opposite, then what to do? That also we'll see in the next slide. Well, now, where the numerical value of M is less than that of MT, the members shall also be designed to withstand a moment ME2 given by. So earlier we saw ME1, now this is ME2. So ME2, it is MT minus M, the moment ME2 being taken as acting in the opposite sense to moment M. So it is opposite direction, where the numerical values of M is less than or equal to MT, that means this value is less than MT. Okay, the beam shall be designed to withstand an equivalent transverse bending moment ME3 not acting simultaneously with ME1 given by. That means we have to design that section for ME1, ME2 and ME3. So ME3 is given by this equation. Okay. Well, now that was related to the longitudinal reinforcement. Now what about transfer reinforcement? So transfer moment and shear carried by concrete. Okay, the reduced torsional moment carried by the concrete TC1 is given by. So this is the TC1, which is equal to TC in bracket E divided by E plus EC. What is that TC? So TC is the torsional moment carried by concrete, T is the torsional moment applied to the cross section under ultimate load conditions. Okay, so where this TC we can calculate from this equation. Okay, in that E is given by T divided by V, EC is given by TC divided by VC, and this value of tau V here, which is required to calculate TC, that is given by this equation, in which FCP is given. And what is that FCP? FCP is the average intensity of effective pressure in concrete at this section. Well, so from this we can calculate this TC1. Okay, now next one, the shear force carried by concrete VC1 is given by, so VC1 is equal to VC into E divided by E plus EC. Well, here how to calculate this? Okay, VC of course we know, okay, and this VC1, E and EC also we are calculating in the previous slide, and we can find that VC1. Okay, now from this we can calculate the area of shear enforcement. So ASV is equal to MT into SV divided by 1.5 B1 D1 into Fy, and ASV is equal to AV plus 2 into AT. Well, how to calculate this AV? So from this equation we can calculate AV, and this AT means this is the equation from which we can calculate AT. Well, now after getting the areas, now what about distribution of the torsion reinforcement? The all transfer reinforcement provided for torsion shall be in the form of closed stirrups perpendicular to the axis of the member. That means just simply you have to provide stirrups only. The spacing of the stirrups shall not exceed x1 plus y1 divided by 4 or 200 mm, whichever is smaller, where x1 and y1 are respectively the short and long dimensions of the stirrups. That means width and depth of the stirrups. Each end of the bar forming the stirrup shall be anchored in accordance with IS 456. And next point is, torsion reinforcement shall be continued to a distance not less than D plus BW beyond the point at which it is no longer than theoretically required. Okay, so this is related distribution of the torsion reinforcement. So that's it for today's lecture. In the next slide, in the next lecture, we'll actually design the sections. Thank you.